I think I'll start with, a while ago I was talking to a respected local service provider, and this person said, and I was talking about serverless, just trying to get a feel for what was happening locally, because I've lived in the United States for 25 years until the last 4 years and moved back here to Australia. I didn't pick up the US accent while I was there at all. And when I asked him, about serverless and that, he said, I would never use serverless for anything. Microservices maybe, Kubernetes, yes, but never touch serverless. I was pretty surprised by that comment. So in talking to Matt about what to talk about today, I think it's really important sometimes that we look at complete 100% serverless solutions that really work. And if you go into using serverless, or if you go into a solution right at the start committed to use serverless, in some ways it's much easier than evolving to use serverless. So that's what this talk is about, our experience over the last 8 months, implementing an IoT solution at massive scale, 100% serverless. So I work for embedthis. It's a company I started in Seattle. It's a small company, about a dozen people, headquartered in Seattle. And since I've moved back here, we're building out a development site here, and we'll probably end up doing most of the development here. embedthis is probably the market-leading provider that you've never heard of embedded web servers. We've all got at home like these NBN routers. Well, in America, Comcast is the equivalent of NBN. And Comcast have our embedded web server in all their routers, and it's about 50 million of them out there. HP printers have our embedded web servers in them, so when you point your browser at a HP printer to manage it, you're talking to one of ours. Sharp photocopiers, Hikvision cameras, which is a bit of a problem at the moment, but also people like Lockheed Martin, Rockwell, Boeing. So we've got a really good base of companies that have put our embedded web server, and this is local management. Hundreds of millions of devices, over 500 products. A lot of those were open source. A lot of them are now commercial. But we really needed to evolve that to manage devices from the cloud. In the past, you could manage locally. People now want the option, and it has to be optional, to manage from the cloud. They still want the device to work if the internet goes down. It's no good to say, oh, well, I can't unlock my house, or I can't use my photocopier or my printer because the internet's gone down. But often you can give great benefits by connecting to the cloud, so it's got to be optional. But the problem is embedded management's really hard for device builders. They're experts in their product. They're experts in an ultrasound machine or an MRI machine. They're not experts in they might be experts in embedded, but they're not necessarily experts in networking or cloud or security or UI UX design. And you've got to be able to do end-to-end to get something running in the cloud. So it's really hard. And just like observability platforms that we heard from the previous speaker, there's way too many of them. There's way too many IoT platforms. And fortunately, AWS and a few others are now, the Goliaths have got AWS platform, have got IoT platforms. And that's a really good thing. The problem is the building blocks. And it's the classic AWS problem. You get a bunch of fantastic services, but they're really low level. And so for a device builder who's not an expert in there, they have to go to a service provider, and I'm not speaking ill of service providers, and they have to connect their wallet to a vacuum cleaner and pay a large amount of money to get a complete IoT solution. When that service provider goes away, they really struggle to manage it sometimes. So that's the problem that we've tried to solve. We want to create a solution, but we don't want to be an IoT platform. We want to do it on top of AWS, because we're just a small little company. They're the giant who's got the infrastructure worldwide. We want to simplify the process so that you can create a device cloud regionally anywhere in the world in seconds, well, minutes, instead of days or weeks. We want to lower their risk, and we want to leverage AWS strengths, and basically want to do all the AWS configuration end-to-end for them, and to do it through a convenient UI. We have to scale from one device up to hundreds of millions of devices. linearly, because there are customers who have that many devices. It has to be zero cost at idle, so they have to be able to put the agent in their device, and if they don't connect to the cloud, there's got to be no cost to them, and there's got to be no cost to us, or virtually no cost. So if someone wants to put it in all their devices and none of them connect to the cloud, that's fine. If they want to have 1 million out of 100 million connecting to the cloud, that's got to be fine. And it's got to scale as fast as possible if for some reason there's a big event and a lot of those devices want to do some management all at once. Fortunately, AWS IoT does that really well. We had a wish list to it as well. Data has to be under the customer's control. And we got this from our SenseDeep observability tool that we created, where all the data is in the customer's AWS account. Now, if you're a device builder in Europe or in Germany, in the UK or the US, the government's now mandating data must remain locally. It can't get shipped out. So doing IoT, we have to regionalize the data. It can't go through our servers. Now, we don't want it to go through our servers because that's costly. We want it to stay in their servers and in their AWS account. So we say we orchestrate, we don't transport. We set things up and then let the customer talk to their AWS cloud. Their costs scale then linearly with their data volume or their data resolution. If they want, every second to be sending state, that's going to be costly. But if they, just want to update once a day or when state changes, it'll be negligible cost. We also wanted to provide a higher level of integration. We wanted to transparently synchronize data. So we wanted to take DynamoDB data from the cloud and sync it transparently, no code, into a device and vice versa. So this is what the solution looks like. You have devices with an IoT, the product called Ioto, with an agent, and you've still got the local management talking to that over HTTP in a browser. You've got our Ioto service, which configures and creates device clouds for the client. The client says, I want them in Singapore, I want them in Sydney, and we'll create and configure the device cloud. When a customer purchases a device and they boot it, it talks to our service and we assign it to a device cloud. And thereafter, all communication is between the agent and the device cloud. And of course, there's a device manager, which may be mobile or it may be a single page browser app. And then we provide a single page device builder to manage the service. All of that is serverless. These two apps on this side are single page apps written in Vue.js. And the device cloud is really where I want to focus of how we've architected that and the trade-offs and the design decisions we've made. The Ioto service is a traditional SaaS site, billing, subscription, downloading software, and a whole lot of other things to support the UI. And that works really well as well. But I think I'll focus on the device cloud. So I'll skip the builder. So the job of the device cloud is to communicate with the devices. Maybe one device, maybe 100 million devices. It stores device data, which per customer is going to be totally different. You may just have a moisture sensor in the ground, or you may have a whole network router with complicated schema and data. We can't control that, we can't dictate that, but we can provide a database that they can store their data in. We need metrics, lots of them, not a few, because people want to be able to compute metrics on all sorts of fleet-wide things across their device pool or individual devices. The device manager has to be white-labeled and branded, and we do all this injected into their AWS account. So the customer has an AWS account in a region, and we inject these components into their account. So they start with a bare account. It's not like, their personal play account with all their junk that they've left there in their AWS account. We want a clean AWS account, and they install this in. So we have to be minimally intrusive into their account because they're going to add their logic into it as well. So it ends up being a collaborative solution. When we create a device cloud, these are all the services we provision. And this provisioning takes probably about 4 minutes. So we create 2 databases, 2 DynamoDB databases. We need change triggers, so we create DynamoDB streams. We configure IoT Core for MQTT messaging. We create 2 Lambdas, SQS for queuing. We create CloudFront for the manager user interface, their device manager interface. Custom domain, Route 53 certificate manager, API gateway for the REST API. Their software images get stored in S3, CloudWatch logs and CloudTrail, and we provision all that directly through the AWS SDK. What it roughly looks like at the end is we create 2 key services that are single Lambdas. They're monolithic Lambdas, a hub and a manager. The manager is for the user interface, and the hub gets talked to by the devices and by our builder service to orchestrate things. So why don't we use CloudFormation? Why don't we use this new hot CDK that seems to be all the buzz? You know, we had choices. We could use Terraform, we could use CloudFormation, we could use the CDK. What we required is we had to fully provision all those services before, all those services. It had to be 100% automated quickly. It's no good sort of saying, well, go away and this will take a day and it won't quite work and we'll walk you through it. It had to work reliably. It had to recover from failures and manual mistakes. In other words, this is their account. So they may have something else there that causes it to break, or over time they may make a change that breaks it. And so we've got to be able to recover and repair. CloudFormation, while being trusted and standard, can be really brittle. Sometimes you get into situations with CloudFormation that you can't go forward and you can't go back. Something will be, its state and reality of state are different, and they don't agree, and the only way to repair it is to remove it and then go forward. And we've had a number of those situations. It doesn't handle out-of-band changes well, and it doesn't handle really complicated provisions on a repeated basis. You know, you do get just strange things that happen sometimes. The CDK uses CloudFormation under the hood, so that doesn't solve any of those problems. And Terraform can be even more brittle and lags AWS in features. So what we did is we used the SDK directly. And I Googled around about this, you know, is anyone using this? And the pervasive wisdom is, no, it's not recommended. That's not what the SDK is for. But we found it's worked great. You know, in the, sometimes the actual code that you have to write in TypeScript to drive the SDK is less than you have to write for the CDK, and certainly less than you have to write for CloudFormation. So some of the infrastructure's actually been really quite terse to create using the SDK. The SDK is really stable, and it's reliable, and it's really well documented, and it's the most current thing for AWS. When they release features, they release them in the SDK first. And we still use CloudFormation right at the start, because when we need to get an IAM role in their account to get permission on their account. So we use CloudFormation to get that proper authorization in their account. Then we flip over, that CloudFormation puts one Lambda in their account, and then we use that to drive the provisioning of all those services. And what the services do, they're done in an idempotent way. We sort of say, is this infrastructure there? Is it configured right? And it may be multi-part that you have to, like the DynamoDB table has to be installed, then it has to be configured, then it has to come online before you can add the streams. Now, the table might be there, but the streams may not. So it checks the state that is the actual state, and then it applies the configuration after. The end result is it's really reliable and it's really fast. we found it actually to be quite a good experience. So if anyone has custom needs, don't be afraid to use the SDK directly to create infrastructure sometimes. So our next big design choice was the database. We needed zero idle cost. If there's nothing going on, it had to be zero. We had to scale from 1 device to 100 million devices. And that means some customers have a large number of devices, some may only have one. It's got to be cost effective at both extremes. We can't have a large fixed cost that means that a small scientific program that's got just a dozen devices won't cost. And we wanted to fully replicate device data out into devices and back into the cloud. So that made other choices other than DynamoDB hard. You know, we've used RDS in the past a lot. It's got a lower read-write cost, and that's an issue with DynamoDB. It has quite a high write cost. And if the devices are writing a lot of data, that can get expensive. We provide tools to the customers to, to minimize that write cost and to minimize their writes. But DynamoDB, it is zero at idle, it's zero setup cost. We can create the table and it costs nothing. And when I say zero, I mean so few pennies, such a small fraction of a cent, it doesn't matter. It's really simple to create, it's very simple to manage, it's not intrusive in the customer's account. And it's schemaless, which means you can have any kind of data there and you're not constrained in terms of the approach. Now, I'll talk a bit more later. We use single table design and we use OneTable, which is a way of managing schemas in DynamoDB. So we can actually give the benefit of schemas in a single table design in DynamoDB. It is harder to query. That's the weakness. So a couple of things. Early in our journey to learn serverless, we created an NPM library called OneTable that we use internally so that we can do single table designs in a more human kind of way, because single table designs sometimes get pretty difficult. It gives you a high-level application entities that you can work with in your code, and they get translated into DynamoDB statements. But it's got a couple of nice things that work for us. You can map attributes, so you may have customer address, for example, and when it actually writes it to the database, the attribute will be CA, and it'll do those translations for you to really minimize your storage. When you've got a very large number of entities, you need to really compress your data, and that helps. And DynamoDB's got streams for replication. Just briefly, that's what the schema sort of looks like. You specify your application models, you say what the keys are, you say what the attributes are, what the type, whether it's required, and the keys get interpolated from other attributes, which uncouples the keys from your actual attribute data. IDs can get generated. It's just got a whole lot of things to make it really elegant to work with. So the next key thing for us was database replication. We wanted global tables into devices. That's what we wanted. We wanted to be able to write data in DynamoDB and have it just appear in the appropriate device. We wanted to write data in the device and just have it appear in DynamoDB. And it does that in a fraction of a second. Okay, it works exceptionally well. DynamoDB Streams is a really simple interface. You get the record as it was before and what it is now. You can subscribe to these, they get passed to your Lambda, and we simply get that data, put it in MQTT and send it to the appropriate device. And coming the other way, we created an embedded DynamoDB which has the same structure as DynamoDB, but embedded. It's got the same, key and hash, and use red-black trees for the actual sort key equivalent. And we've got the same kind of triggers, so we get a change record that we put into MQTT, push up to our Lambda, and it then applies it to the database. Now, there's a whole lot more complexity in replicated data than that, but that's the essence of it. MQTT is one of these great services. It's really low cost. It's exceptionally efficient. We do catch up, so if the network goes down, you catch up on the data that you missed at the server end. If the device gets rebooted, it catches up with data that hasn't gone to the cloud. But the beauty of this is, if you're on the device, you just put data in the database. You don't even have to think about it. And then at the cloud end, you can hook in triggers to run Lambdas in response to data changing. And similarly, in the device, when commands get sent down to the device, you can have triggers on your device to respond to it. You don't have to worry about packaging up MQTT messages, sending them. All that plumbing's done from you. You just do triggers at either end with Lambda or C code. So it really reduces the code that device builders need to write. That synchronization is controlled again through the schema, and you can say, like, this is an example of a system application entity in the database. You can say, does this entity live in the cloud or does it live on the device? You can have entities that only live on one side. In this case, it lives on both sides, but it synchronizes up. So changes on the device get pushed to the cloud, but not from the cloud to the device. It's generally good practice not to have synchronization going both ways. You can have default notification, which uses Event Bridge to create events based on change data, which anyone can hook into. And you can also trigger metrics to be automatically created for you into CloudWatch. And that's the next problem we encountered. IoT needs extensive metrics, lots of metrics. One device may have 10, 20 metrics. Fleets may have, multiply that out by how many devices. But CloudWatch metrics are damn expensive, custom metrics. In our SenseDeep observability tool, we were looking at this company, and they hit a problem, a scale problem. They were paying $700,000 for CloudWatch metrics per year.
That's more than Microsoft SQL.
It's unbelievable. CloudWatch metrics are $5 per metric per year if you're using it, if you update it or query it every hour. So for us, you know, what's fantastic about CloudWatch metrics is if you don't update them that much, then they don't count. So it may be cheaper than that, but for active metrics, it's just prohibitive. And the reason is they support arbitrary intervals and arbitrary and really high resolution. So you can say, you know, January 1st at 9:07 to January 1st at 11:15, how many of those, you know, did I have in that period? Whereas devices don't need arbitrary resolution in most cases. What we need is last period metrics, last hour, last 5 minutes, last day, last week, last month. That's a much easier problem, and it requires a lot less storage. So our solution, which we're going to release as a library, is better AWS metrics. And these are literally 1,000 times cheaper or run at least 10 times faster. You can store, they get stored in any DynamoDB database table. So it can be in your own existing table with your own existing apps. And it uses prefixed keys, and you can have different domains, which we refer to as the owner. So you can have different services or different applications or whatever is the owner of the metric. And then it follows the CloudWatch namespace metric dimensions and interval, and that's the sort key. But what's beautiful about this is updating a metric is one write. And as an interval, let's say you're doing 5 minutes, just for argument's sake, 5 minutes, 1 hour, 1 day, and you can custom pick what those intervals are on a per metric basis. When the 5-minute buckets overflow, then you get a write to the next up interval. So you're getting basically one write per update, and then when that overflows, you get 2 right. So it's really inconsequential in terms of the right load that you get. It's extremely fast to query, and you can query and say, give me a list of the namespaces by doing a query with a sort key, begins with sort key hash, that'll give you everything, or begins with sort key hash namespace, and it'll give you the metrics for that namespace. So just by using different key prefixes, you can zone in on the metric that you need. We prune them with using the TTL feature of DynamoDB so that the old metrics automatically get erased. You may decide I only want metrics to live for 2 months and then I want them to disappear. We use this on our own website to track dwell time on people reading blog entries. And we only wanted to see it for a month or 2, and then the TTL just erases those entries after that. And it's only about 500 lines of code. It's pretty simple, really easy to read. So we'll be releasing that sometime over the next month. The end result is devices can have any number of metrics they want. It's not cost consequential for us anymore. And customers can specify it in their database schema. I won't say much about Lambda, except we've done a couple of things different. We have a monolithic pattern. We have 2 big Lambdas, and the reason for that is we couldn't inject hundreds of Lambdas in a customer account. That would make it hard for them to work in. They want to see Ioto Manager, Ioto Hub, and that's it. And that's what they see. Instead of using Express, we wrote our own custom controller. It's a bit faster. It has no dependencies, so it's better for security. A monolithic pattern helps with cold starts because it's only one function that's going to be running. And you'll occasionally get cold starts at scale as you start scaling up more, but the number of cold starts will be smaller. So for a single page application, you don't tend to hit and then get 4 or 5 cold starts. You might get 1, and that's it. So our UIs are really responsive as a result of that. We use the serverless framework to deploy. Deploying one of these, I've just measured it this afternoon, it takes 1.9 seconds to deploy. So deploys are really quick. And we have some long-running Lambdas that will run 10, 20 minutes, and they'll do things in batches. And they just do a batch, and they'll come back and do a DynamoDB query from a particular thing to pick up the next bit of work. We don't use queues for that. Lambda's cheap, so we lean into it. It's really simple. The other thing we use dynamic logging control. We believe in rich JSON structured logging. The sense logs library we use has the ability to dynamically change the verbosity of logging. So you can change an environment variable, and when the next the next one that gets invoked will run a different instance with a changed environment variable, and the logging library will change its verbosity without redeploying. So that's really helpful. We can have a problem we see in the logs, and we can say, now we want to turn logging up to the max, or we want to turn it on in that module or in that function. And we can, so we put in lots of logging that's there all the time, but it's no cost because it doesn't get invoked unless the environment variable turns it on. So that's really useful. So the key decisions that I think make our solution a little unusual, we use the SDK, not CloudFormation. We use monolithic Lambdas. There's nothing wrong with monolithic Lambdas. There's trade-off. It's not as granular. The purists may not like it as much, but it works really well for us. We use single table designs and find that if you do the thinking up front and the single table design up front, they can work really well. DynamoDB streams are great. MQTT is great. And extensive JSON logging. I'll just say, what we really found is leaning into the AWS services that work really well is worth doing. lean into Lambda, lean into DynamoDB. Don't expect it to be RDS, but lean into it and use it the way it's meant to be used. But also recognize the AWS services that are really not good, like CloudWatch. And it's not just metrics. You know, they're good in their role. And don't get me wrong, CloudWatch logs, universal, save the logs. But you've got to know the limitations. You know, there's some things that really work well in AWS, and it's worth leaning into those and use them the way they're meant to be used and use them hard, and identify the parts of AWS that don't work as well, and don't be afraid to invent around them and invent your own stuff around them so that you're not struggling with them. So it's early days. We launched this in Q4. We now have 600 builder accounts created. We're getting about 30 user sessions per day. We've put through 200K worth of revenue through it so far. Our running cost is less than $10 a month for the whole thing. That's the Ioto service, setting up the device clouds. We don't have any customer with really large number of devices yet, but because they go through their device cloud, it's going to show up on their bill, not our bill. And that's not because we're trying to weasel out of it. We're trying to, you know, the cost is going to be there, but they can see it and they can control it. And we work with them to be able to manage that. But our costs for this service will stay exceptionally low. And that's it. Any questions? Oh, I should give my, my contact details.
I've got one. Do you have any, you've got management infrastructure, I'm guessing, on your end?
Human or infrastructure?
Oh, both. Operations, do you have much of an operations team, and how much infrastructure do you have to run to be able to manage all them? Do you have like agents or anything that probes the status for your customers' infrastructure to see how well it's running?
The device cloud reports back to the builder key metrics on a daily basis. And so it reports back a package of information. And that includes errors logged, it includes devices registered, amount of traffic going back and forth. So they get their metrics and we summarize some of those. We have to be really careful with that because of their jurisdiction of data. But it's more just enough for us to know that it's operationally working correctly. We encourage them to use all the observability. You know, ultimately, they have to run. They'll be injecting their Lambdas, their business logic. They'll be hooking into data. And so they need tools directly in their device cloud as well. We're not yet providing, you know, observability for totally in their cloud for their code.
Definitely made me face some of my own biases. I have a question about, I'm just not 100% convinced about the CloudFormation argument. I understand, but you identified Drift as kind of the main issue with CloudFormation for you as the reason why you use the AWS SDK. But if that's the core reason why you went kind of in that direction, how do you deal with it yourself? Because Drift will exist regardless. If people start manually changing things, then how does your system compensate for all of that?
So the main issue for us was, Drift was one, the main issue was the brittleness. We and ourselves over the last couple of years got into a number of situations where couldn't go forward, couldn't go back. And we had to recreate things, had to remove some infrastructure and recreate, and had to manually go through that process. Sometimes that happened through just cosmic rays or whatever, you know, just something went wrong and don't know why. Couldn't explain why, but couldn't go forward, couldn't go back. So we just couldn't have that. CloudFormation is very safe. It's very do a step, double check, do this, do that, etc. And so the slowness was also an issue. Configuring all those services in, and its sequencing is is very, very conservative. You can do more in parallel in our use case. So we knew exactly what we needed to create. I'm not saying this is a general solution, but we knew exactly the infrastructure we needed to create. We knew exactly what could go on in parallel and what couldn't. So we're able to craft. And the end result is the customers will get a better infrastructure build out than if we'd used CloudFormation. If we'd used CloudFormation, that would have been exposed to them. And when something goes wrong, we'd be saying, look at CloudFormation in your account and tell us what it says on that. Whereas we can wrap the whole thing, we're building it, so we get the error reporting directly back to us, and we control that build process really tightly. So it's really a set of things. The takeaway that I wanted to communicate is, if you've got a need for a surgical bit of building out infrastructure, absolutely believe in infrastructure as code, but it doesn't have to be, it can be via the SDK if you've got that use case to justify it.
This is one of the biases that I was talking about that I had to face
Yeah.
during your talk.
Yeah.
Can I just quick follow-up?
Sure.
You mentioned that Lambdas are provisioned via serverless framework,
Yep.
which is CloudFormation, really, right?
Yep, totally.
Do you kind of see any issues, because you will have buckets and Dynamo and other things that are referenced by those functions that are then provisioned by CloudFormation, so you have dependencies. You may have an interesting dependency structure which could become circular as well. Something has to exist before function is provisioned.
Yep. So
See any issues with that?
we only use serverless framework to deploy our Ioto service, not the device clouds. The device clouds are all done through the SDK. The Ioto service, it's a SaaS application. It's just what's running the builder. It's totally controllable. Customers don't trigger it. We do deploys when we want to do deploys. So, and we do the classic, QA, beta, test sites, etc., and production. And so serverless framework is really simple. We've got a really simple app. It's the same, a set of monolithic Lambda functions based around per controller. There's probably 14, 15 of them. And so we pre-provision the database and all the other infrastructure that we need. That doesn't change. And then when we do the serverless framework deploys or updates, it's just plinking individual functions.
Makes sense.
How are you handling updating infrastructure on the client side in terms of deploying changes to those Lambdas you put in their accounts, like the hub Lambda, for example?
Good.
Or just don't need to do it?
Good question. When they create the cloud, it goes through and does all that creation. If they come back in and edit the cloud and they can say, I want to update the code there. And it's split into the hub function, we control that, we update that. The manager one, they can stay on a set version and they can sequence their version. Typically, we encourage customers, put your code outside, and so we decouple that, they hook in via Event Bridge. So it's somewhat separate, their logic is separate, and then those two functions have very defined roles. Each day, the hub, the Lambda, we have we have a CloudWatch schedule that will fire off the hub Lambda as a separate instance. It'll get a schedule event. It'll say, oh, okay, I'm running the schedule persona now. I've got to do my daily schedule things. And one of the things it's got to do is use the update function code API. So it does that, and then the next invocation will be the new code that comes. So that's sort of transparent. If we've published updates, the device clouds around the world will update themselves when they run their daily schedule.
You mentioned using a monolithic Lambda approach, and you mentioned that there's sometimes sort of 10 to 20 minute runtimes. Are you using step functions and fat Lambdas to achieve that?
No. I look at people with respect and bewilderment who like step functions. So, and it may well be the same way that someone from an enterprise background looks at serverless people and says, oh, they're serverless people, I don't quite understand it. So I haven't done enough with step functions to be competent to pass any judgment on it. Basically the kind of long-running, we have to do some database maintenance and things like that. And so we do long-running functions, and we just, a lot of that doesn't even need to save state, because once we've processed something in the database, when we next come around, we can query, and the query will return the next bit of work to be done. So we drive a fair bit of that from the database. We do have a bit of state, and we'll record where we're up to with state in DynamoDB. And when it next gets invoked, it'll pick up the work from where it needs to. We use SQS, I've just forgotten where, somewhere for queued work as well. I'm not quite sure where at this point. You know, step functions could be good, but it'd just be another service we have to understand, and we don't understand it yet well enough. Maybe that's another.
Well, if what you do works and you have paid customers,
Yeah.
actually
That's it, yeah.
No, but you can do that, and there still can be a better way.
you can slowly optimize.
I actually like that comment you said, where this is one of my paradigms, and one of the things I tell teams is, if you don't understand how the managed service is going to work and operate, you shouldn't be using it.
Yeah.
Because you need to understand how it scales, how it fails, and how it does actually work. And I think that's what you just said about step functions is very valid, in that if you don't understand all of those other paradigms of that service, it becomes difficult to reason about what's going to happen.
And I think that's really key, to lean into the services that you understand and work really well for you. You know.
Thank you. Thank you everyone for coming. Thank you